Hey everyone, welcome back to the xHCI driver development series. In the previous episode, we were able to determine which xHCI ports are USB2 versus USB3, so in this part, we'll focus on actually resetting and preparing the xHCI ports for handling real device connections. Without further ado, let's get started. Now imagine that this is your computer. There's a motherboard inside and a case around it. Somewhere inside on that motherboard, there is also an xHCI controller. Now on that controller, there are numerous xHCI ports, or more specifically, port registers. Now also imagine you have some devices, like a mouse and a keyboard, that you plug into your physical USB ports on your computer, and those physical ports map to some xHCI port registers. It's also important to mention that each xHCI port is actually backed by several different port registers, but in this tutorial, we'll only focus on PORTSC, or Status and Control Register. So as we mentioned in the previous episode, the ports are divided into USB2 and USB3 counterparts. And depending on the type of the connected device, a different port register set may be used to service that device. For example, if you unplug your old USB2 mouse and plug in a super speed USB3 mouse, the connection will now go through one of the USB3 port registers. Now, whenever a device gets connected to a port, or the controller is reset, we, or the operating system, have to reset that xHCI port, and the procedure to do that can vary slightly depending on whether the port is USB2 or USB3. So with that explanation out of the way, let's get coding. The first thing we're going to do is go into xHCI regs.h file and create a struct for our port status and control register. I'm not going to go over every field now, but I tried to properly document each one, and will leave a link in the description to this file explicitly for you to refer to. An important thing I will mention though is that some fields are marked as r/wc, which means read or write to clear, which means if a value of 1 is written to that register bit, it will trigger an appropriate reset action and reset that bit back to 0. Cool, let's now go to our main xHCI.h file and create a couple useful functions. First, we need the ability to read the port status and control register for a given port. And that port is going to be 0-based. So the first port in the controller is port 0, the second one is port 1, then port 2, and etc. After that, we also need a function to write a new value back into the PORTSC register, also for a given port. Awesome. And now let's declare the primary function that this tutorial is about, called resetPort, and it will also take in a 0-based port number as an argument. Cool. Let's now go into the xhci.cpp source file and implement these functions. In order to access the xHCI port registers, we have to use the following formula. First, we take the operational register base address, then add the port register set offset, which is 0x400 or 1024 in decimal to it, and then index into it by multiplying the 0-based port number by the size of each port register set, which is 16 bytes or 0x10 in hex. You can refer to my main StelXOS's GitHub repo to see the definitions for the other port registers in this set, but for simplicity, we're only using the status and control register here. Alright, now after calculating the PORTSC register base, we can read from it using a single 32-bit dword read. And that's it, very simple. Now we're also going to do almost exactly the same for the write function, except instead of reading from the register base, we'll write into it using a 32-bit write. Cool. Let's now go to the end of the file and define the reset port function. Let's start by first reading the current value of the status and control register from the controller. Then we'll also store whether this is a USB 3 port or not in a local variable, since we'll need it a few times. Alright, now we can start our reset sequence by first checking if the port is powered, because if it's not, we should power it on. So if the port power bit is set to 0, we can set it to 1 and then write it back into the controller. Additionally, we'll give it a 20 millisecond delay to let it process. After the port powered on, don't forget to read the value of the PORTSC register back because some other bits could have changed due to the power on action. If after requesting the port to power on, the port power bit is still set to 0, that means something went wrong and we should return false, as the reset has failed. Now remember how I said that some bits are marked as write clear? Well, PORTSC register has a few status change bits, such as connect status change, port enable disable change, and port reset change bits, all of them being write clear bits. Before resetting the port, we should clear their values as they might be stale from either previous resets or other port operations. And we can do that by setting all of them to 1 and writing that value back into the controller. On QEMU, this isn't much of an issue, but I found from personal experience that on real hardware, this is very much needed. Cool. Now we can actually initiate the reset sequence for the xHCI port. If the port is a USB 3 port, the xHCI can do what's called a warm reset, which is generally faster than a full standard reset. And we should set the warm port reset, or the WPR bit, to 1. Otherwise, if the port is a USB 2 port, we have to set the standard PR, or the port reset bit, to 1. After that, we can write that value back into the controller. Now this will trigger a port reset sequence within the controller and should take at most 100 milliseconds. So we can use a busy loop with a timeout approach to wait for the controller to indicate the successful reset, which for USB 3 ports would set the warm reset change, or the WRC bit, to 1, or for USB 2 ports, it would set the standard PRC, or the port reset change bit, to 1. If we reach the 100 millisecond timeout, but neither of those bits were set, port reset has unfortunately failed, and we have to return false. Now here at the end, after those bits get set successfully, I've also seen that on some hardware it's also good to let the controller stabilize and sleep for another few milliseconds. Finally, as the last step, we have to once again clear the status change bits, as well as the reset completion bits, and of course, write that value back into the controller. Now here is a big caveat that tripped me up when I was first writing the driver myself, and that is you have to set the port enable disable, or the PED bit, to 0, because it turns out that the PED bit is also a write clear bit, meaning if you write a 1 to it, it will clear it to 0 and actually disable the port when you write the value back to the controller. But after resetting the port, the controller itself sets it to 1, so when we read it and then write it back, we have to make sure that we don't write that value of 1 back into it and accidentally disable the port again. Please make sure you don't miss this. Alright, cool. Now we can give the controller a few milliseconds to stabilize again and read the latest PORTSC register value. Now the PED bit should be set to 1, indicating that a port is enabled. But if it is not, that could happen in the case when the port got reset on a device disconnect event, and no device connected since, and now you're trying to reset it again. Otherwise, in most cases, if the PED bit is set, that means success, and our port has been successfully reset, and we can return true. Alright, now before we go and use our reset port function, I want to have a little bit of fun and write a cool little function to take the speed value from the PORTSC register and convert it to a string representation of it, so that we can print out the speed of the connected devices. Awesome. Let's now go back up to our start device function where we previously printed out what type of ports we have, and now let's check for which ports have a device connected to them, which we can do by reading the PORTSC register and checking the current connect status and connect status change bits. If both bits are set, then a new device was connected and we should reset that port. If the port reset was successful, we can print out a neat message about the speed of the connected device, for example. If the port reset failed, let's also print out an error message. And that should be it. We can now go and test it out. Also, a reminder, make sure in your QEMU flags you specify at least one USB device via the -device flag, like I do here with a QEMU mouse and a keyboard. Otherwise, you will not have any ports showing a detected connection, and you will be sad thinking your driver isn't working when in fact you just don't have any connected devices. Now that we have that done, let's recompile and run the project. Amazing! As you can see, we now have ports 4 and 5 reporting a device connection, and both have a high-speed USB 2 device connected to them, which checks out based on my QEMU flags. At this point, I want to say congratulations if you made it this far, because this officially marks the first half of the series where we focused on all of the tedious and maybe sometimes boring parts of setting things up. But now that we have both the controller and the ports correctly set up, we can proceed to actual device initialization, which will be super cool, involved, and feel the most rewarding. I also want to apologize for taking much longer time to release this episode, as I got a new job at a startup and had to move across the country, and in general had extremely little time to work on editing the videos. However, I really appreciate your guys' support, and some of you even contributing to Stellix itself and finding the potential mistakes or edge cases in some of the code. Seeing people actually benefit and enjoy these tutorials is the biggest form of motivation I can ask for. On that note, I hope I can get back to faster release cadence soon, and I'll see you all in the next one.